Welcome to the final session for today. The speaker is Robert Mybus from Internet in Adelaide, and his topic is After Arduino. Thanks, Robert.
Hi everyone, so thanks for coming along. As you can see, you've got my Twitter handle there, so if you want to hurl any abuse, it's okay because my phone is on silent. So, why might you want to come and pay attention in this talk? Well, really, you're all going to be, I presume, fans of Arduino and Arduino type devices. So, one of the things that I found about them was that they're a little bit more expensive than I'd like. They're not outrageous, and if you have a really good idea in mind, particularly something for your employer, you can walk up and you can say, I want a Freetronics Leo stick or something like that, $30, easy to justify. But I can just imagine the conversation if I go up to my wife and say, I want to buy half a dozen of these things to do stuff for my hobby with, and she'll say, oh, okay, what are they for? And I'll try and explain it and fail miserably probably. And then she'll say, oh, well, what are you going to do with it? And I'll say, well, stuff. Because that's what you do with them, right? So, I wanted to find if there was a better way, a way that I could make it work and not have to worry about dropping quite so much on each individual little board. Because I love them, they're great, but just a little bit more than I'd like to be paying for them. The other thing is that there's a number of limitations of using Arduino, like only being able to have interrupts on a couple of pins, or only being able to do PWM on some pins. And sometimes that's just really, really irritating. And it turns out you're not actually limited because of the hardware to doing that. It just happens to be easier to do it the way that Arduino has done it in the hardware. There might be other reasons too. So why might you not want to do this? So the absolute obvious reason is just complexity. It's a little bit more work to set up, it's a little bit more work to do, you can't lean on as many of the Arduino libraries that exist out there, and it's just a bit more of a hassle sometimes. So what is Arduino? I mean, what are we actually talking about being after Arduino? We have to know what Arduino is. Arduino is a whole bunch of things. So the first and most obvious thing is the hardware, the really distinctive, lovely, pretty blue boards, and the open spec that goes along that, so that other vendors can go and contribute other board designs and other things that suit their particular needs. It's an IDE. It's also a bootloader that runs on the AVR chips that come with the Arduino to allow for easier code upload. And it's a series of libraries that get compiled in with your application to help you write software easier for that chip. And finally, it's community. Things like the Arduino forum. The hardware is, as I said, it's easily recognizable, but what really is it? What it is, it's a development board to help you get started with learning how to program the microcontrollers that Atmel make. And there's actually competing boards from other manufacturers like Texas Instruments that you can go and buy for a very nominal sort of cost that you can do very similar sorts of things with. You can flash blinking lights on pins and look at buttons and all that sort of stuff. And that's an example of one that I've got at home as well. And you can get them from a lot of different manufacturers for a lot of different chips. Previously, they did seem to be always a bit more expensive, and the Arduino has helped drive that down into the hobbyist market. So here's some examples of some basic Arduino boards that I looked at, trying to see if I could find a cheaper way of buying one at least. And for the most part, no, but the last one really caught my eye. Breadboard Arduino. On the wiki, on the Arduino.cc wiki, there's a page about how you can actually use a breadboard with a little 0.1 inch spaced pins in it. So you can just put a AVR chip in there, put all the supporting infrastructure around it, and then build your own Arduino like that. And I thought that looks really cool. But you still need to go and get all of these extra components. And, well, in addition to being a bit cheap, I'm also a bit lazy. So you can actually look at the specs and the data sheets and the design documents for things based on Arduino. So this is one from the Arduino Pro. And once you actually remove all the things that are just connectors, you get left with what's really important for the people that build them. And for the most part, it's not actually that interesting. So you have the actual MCU. It's the brains of it, right? So you've got your CPU equivalent, your memory, your flash storage for your app, and some EEPROM for storing data on it. You've got a power regulator, but, well, normally they say don't do this at home, so this is the only do this at home, right? I don't really care if I get between 4.9 volts and 5.1 volts. I'm not trying to save the earth or run medical equipment, so some sort of variation or the occasional crash is okay for me. So I don't need to worry about running a power regulator, or for that matter, power smoothing capacitors to make sure it's nice and flat. I know that I'm going to provide 5 volts from my USB, or at least close enough that I don't care, or that I might provide 4.5 volts from a few AA cells, or something like that. Obviously, you've got your little flashy blinking lights on the board that say it's communicating, or pin 13, or all that sort of stuff. Well, I definitely don't need those. And a reset button, well, my code never crashes. The other major thing, and this is a fairly important one, is a crystal oscillator. So there's a little bit on the board that helps define the clock rate for the processor. And with that clock that's external, it's a high quality crystal, means that you can push the chip faster and faster and faster than you can without one. But it still works without one. And the last thing, which is on some boards, is USB connectivity. So that's the breadboard Arduino that I mentioned before. It also has a minimal configuration without any of that supporting stuff, UBU. And it just needs a custom device added into the Arduino software. So if anyone remembers from the Leo stick last year, you had to open a text file and add a few extra lines into it so that you could actually compile and run apps for the Leo stick. It's the exact same thing. It's about 1 minute's work to add that in. But how do you actually program it? So without being able to have USB upload, you've got to have another method. So there's a way of doing it called in-system programming or in-circuit serial programming, which for an Arduino device happens to run over the SPI or serial peripheral interface bus, just to throw all those acronyms in. And it's the little 2x3 header that you see on a lot of the breakout boards. So you get something like that, USB on one side, and the SPI on the other side, and it lets you actually rewrite the flash in the Arduino clone that you're building without having to have a serial upload mechanism or a bootloader already on that chip. So there's a bunch of different ways to do it. One is that you can buy one like I did. You can buy a whole bunch of different types of them. There's several different sort of classes of the device. You can get really professional, expensive ones. You can actually just upload a particular sketch to an Arduino that you've already got, and then use that to program a chip to make another Arduino. So once it's in a breadboard, though, you need to actually get the pins to the right spot. So once you've got your little cable, you need to plug it in somewhere. And originally what I'd been doing is I'd plugged in my chip into my breadboard, and then I'd gotten little jumper leads and I'd plugged it into the plug, and then I plugged them into the right spots on the breadboard. And I tried and I tried and I tried and I couldn't flash the chip until I realized I'd been holding the plug and looking at a diagram of how the socket was wired. So I'd actually plugged it in exactly opposite backwards, and I noticed this when it started to smell and get rather hot. So the other thing you can do if you're looking at custom devices is the high-low tech group at MIT has actually gone and ported those Arduino libraries, or at least the more critical and more used parts of them, to smaller devices that are in the same sort of processor family as the 80 mega 328 chip that the Arduinos currently come with. And so out of those, I happen to use the 80Tiny 85 quite a bit. And so it's really, really convenient because it's only an 8-pin package. So it's really, really, really small, but you can still solder it yourself. One thing you do have to do with some of these chips are burn new fuses into them. So what that is there's just a few special bytes in the chip, and you write them with the same software you use to upload a program to the firmware, and they set special options that the chip uses when it's starting up, like, do I use an internal clock source or an external clock source? Do I want to have brownout detection enabled? And other things that you can't alter as the system runs. Word of warning though, if you get them wrong, your chip may not boot until you actually get the right hardware around it to make it work again. If you burn a fuse that says this requires an external crystal, it won't boot without one because the clock counter for the CPU actually never advances. And that's the reason why you can't just take a chip out of an existing Arduino and try and run it in a breadboard without a crystal. because you can't have a bootloader on the really, really small devices because of the limited amount of flash they have, you absolutely have to do an upload with an ISP. So that's an example of one that I did. Just ignore the really, really bad soldering because I was in a hurry. I'd like to blame my soldering iron for being too cold, but you know. Anyway, moving on. So going back to the software as the next step. So it's got the IDE. The IDE really actually calls down to GCC to do the bulk of the compilation. And from there, it calls it over to a bit of software called AVR Dude. I'm sure there's a good reason for that. To actually flash the firmware into the chip. So when you do your Control-Shift-U or whatever it is in the IDE, and that does the compilation, that's using GCC, and it does the flashing, and that's using AVR Dude. And during the compilation phase, it'll use the embedded libraries that get shipped with the Arduino IDE to help compile your program as includes. And it'll use the bootloader that's on your Arduino chip normally to then transmit the new firmware and append it after the bootloader. The IDE is really, really basic, and every time I tried to use it much, I got frustrated. I don't want to get into a religious war about it because everyone's got their own preferences, but I just knew it didn't suit me. So it turns out the GCC stuff is actually really simple to do by yourself as well. So this is an example of compiling a program for the ATtiny13, which is even smaller again than the ATtiny85 in terms of flash resources. AVR GCC is available in packages for Ubuntu and Debian, and is actually really easy to get started with. You'll also want the AVR libc packages so that you can actually compile it usefully and do things without having to do everything in assembly. AVR Dude uses the ICSP mechanism I mentioned earlier in order to actually upload things. So you don't need to have a valid bootloader that you can have serial communication with. You can, and that's an option, but you don't have to. So the embedded software I've mentioned before is the bootloader and the libraries, and the thing that the bootloader gives you is the serial upload. So you might have noticed sometimes, especially with the newer boards, if you've actually got an application running that uses the serial port, when you plug the Arduino into your machine, if the Arduino's got an external power supply and it's already running, you plug it in and it resets itself. And that's because the way that the USB gets configured on the boards is such that it does the reset to run the bootloader, so you can then upload your program if you happen to be running the IDE there and trying to do an upload at the time. Because the IDE will open up the serial connection, and that triggers the reset, which runs the bootloader, so the IDE can talk to it. I hope that just made sense. Because you're not using a bootloader though, that means that you don't have to have the automatic reset if you're doing it all by hand. So the libraries, what comes in the libraries that's useful? Everyone's probably familiar with things like pin mode and digital write. They're the things that you need to say, this is an input pin or an output pin. I want to set high, 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 low, low. And it's always like that. You don't set groups of pins typically. For interrupts, something like attach interrupt, say when pin 2 is rising, I want to schedule an interrupt to this function. With timers, I say timers in this, it's not really the way that when I was using Arduino I was thinking about it, but really it is. There's a clock in the background that's counting along, and when you call the millis function, it just grabs the current value of that clock. And similarly with delay, it just sets up a thing that can wait for the clock to advance the right amount of time. So this is the alternate title for this presentation. Because what it turns out being is that the new approach of, hey, let's do this stuff, you know, that's better than Arduino and more complicated than Arduino and awesome and fun, actually turns out to be the old approach of, well, we've got a chip, let's find the data sheet and we'll read the data sheet. So it turns out the Atmel AVR data sheets are all available for free on the website, no sign-ins, no logins, no one-time only download, no proof of purchase, nothing. So what you should do is you should go and download them and try and read them. They're actually really not that badly written if a regular person to try and read. There's, you know, obviously a decent amount of technical understanding that's necessary to parse it, but I'm sure you can get there. So with I/O, on the AVR chips, I/O pins are grouped into ports. So you have port A, port B, port C, for instance, and inside that you'll have a group of pins, maybe 6 pins, maybe 8 pins. To control them, you have the data direction register, and that's what the pin mode function normally does. The data direction register is just going to be a byte per port, and a 1 might say it's an output, and a 0 might say it's an input for that particular pin. Similarly with the input register and the output register, it's a byte per port. If you read from the input register for that particular bit, it means that that particular pin is high or low, depending on how you read it. And similarly with the output, you set that bit, it goes high. And there's a whole bunch of really, really helpful defines that are all hidden away in very, very troublesomely named headers. So here's an example for port B. Port B is the name of the register that you use for writing out to the port. DDRB is the data direction register for port B. And here's an example of actually using it. So you can see I've very helpfully done the maths on the binary, which I think I've got right this time. And you can see I've set the data direction register to 2, so that sets one of the pins to output. I've set that same bit in port B to high, so that actually sets it to high. And the third example is reading from pin B, or port in B. So that's reading the 0, 1, 2, 3, so the 4th pin that's in the pin B group. And the AND one is just do a bitwise AND, strip out any extra crap that happens to be there. The pin numbers and ports and things like that are not aligned to Arduino pins. In comparison, the Arduino pins can be basically anyway, because there's an abstraction layer in the software in the library. It's all just a bit awkward though. So I don't want to have to do bit maths, and I don't want to have to do remembering register numbers and pin numbers and things. So there's extra defines. So DDB0 is the data direction bit number for port B, pin 0, and DDB1 for the next pin after that, and so on and so forth. And PB0 for the port B input and output pin numbers, the bit numbers for those pins. So that means you can actually rewrite it a lot neater, and now you can actually see that the values make sense. Because it's all binary, you can just do a binary OR to mush the numbers together, or and pack them into the same byte, so you can do more than one thing at a time, which is something that you can't easily do using the Arduino libraries. You have to do, I'm going to do a digital write and a digital write and a digital write to set 3 pins. With this, you can do all of those pins in a single port in one instruction. One of the other neat tricks that you can do is, because we're not using a crystal on this chip anymore, you can reuse those pins for input and output. And you probably should never do this, but it turns out you can also use the reset pin for output. It sounds really crazy and stuff because you've got like all these pins, but on the 8-pin devices, that's actually kind of handy because you've only got a really limited number. Once you've got a power and a ground and a couple of input and output pins, you run out of pins really quickly. So the next section is interrupts. And again, we're back to the data sheets. Have I mentioned the data sheets are really, really useful for this? So each part of the data sheet, be it I/O or interrupts or the next section timers, they're self-contained in the data sheet. You don't actually need to go scrummaging through much of the rest of the data sheet if all you're interested in is I/O or interrupts. So you can read through it. And here's some examples of some of the interrupt names that you might find on a ATtiny85. So PC int, pin change interrupt, timer 0 OVF, so timer 0 overflay. There's multiple timers on these chips, and they've all got numbers the same way that the ports all have names. I'll get to the timer things a bit later. In the actual flash, they're stored as a series of jump instructions. So it's just jump to this function, jump to this function, jump to this function. And what happens is when an interrupt is generated, it just jumps to the appropriate part inside this table, which then has the jump instruction, which jumps to the right place in your code. The net upshot of that is you can actually, if you promise that you're never, ever, ever going to use interrupts, you can actually put your own code where the interrupt table goes and just use it as generic flash space. Probably not a great idea though. So pin change interrupts. So there's a few different registers that you need to worry about to deal with pin change interrupts. So you have the general interrupt mask, which actually says whether it's going to deal with pin change interrupts at all. You have a pin change interrupt control register, which you have, which controls which ports interrupts are enabled on. And then you have a pin change mask, which decides which pins interrupts will be triggered for. The earlier that the chip can decide not to deal with an interrupt, the less power and the less effort the chip is going to use not dealing with that interrupt. So if you have a whole bunch of things, buttons say, that might cause interrupts, and you group them all on the same port, that means you can turn off all the interrupt handling for the other ports. So there's no monitoring of that at all while the chip's in a sleep state. One of the other things about being on separate ports is the actual interrupt routines that get called are separate functions. So if you, for some reason, are really, really conscious of your clock cycles and you don't want to have to check to see which pin actually caused an interrupt, you can just put one pin from port A as an interrupt and one pin from port B as an interrupt, send them to separate function handlers, and you're using less clock cycles to make that decision. So again, and there's the set enable interrupts and the clear of interrupts. You need to put these around things that change the interrupts, because if you want to change the configuration of them, like turning them on and off, or changing what options you might have, because the last thing you want is for you to have a timer overflow interrupt enabled, and then for you to go and change the timer, and partway through you modifying that timer, it goes and triggers an interrupt because the settings are half filled in. The way of actually registering the interrupt is there's a macro called ISR. You put in ISR, whatever the interrupt name is, which is generally just pulled from the data sheet, underscore vect, and then you have a code block. One important thing about the code in that block is it will not be interrupted by another interrupt. So like I said, you can do all the pins as interrupts. In the Arduino library, you can only do a couple of pins on most boards. The downside is that you can only say that a pin has changed. You can't say that it's rising, you can't say that it's falling, and you certainly can't say that it's been eaten by a GRU. Timers. So timers is more than just delays and millis, which is why it's timers and not, you know, sleeps and clocks or something. It's probably the most complicated part of what I'm going to talk about today. It's responsible for how PWM works. So you know you've got some pins and you can say, I want to analog write this, and they'll have different brightness levels on the LEDs and things like that. That's all done through PWM. And what the Arduino library is doing and abstracting away from you when you do that analog write on a digital pin is it's actually setting up a timer in the background that matches the setting that you have there. So if you've done 128, it sets up a timer and says, I want you to toggle every n milliseconds. And then it links it with the output pin that you've just done in hardware, and every however many milliseconds it is, it'll toggle the state of that pin. One of the other things to note is that it can be accounted for an external clock. This is actually something that Bunny touched on in his presentation this morning. He talked about possibly being able to use the clock source from the incoming video signal to do something with his project. So this is something you can do with that. You can actually say, for this particular timer, I want to use an external clock, which might be, say, a 60 hertz clock or a 50 hertz clock to sync up with your incoming input signal. So the timers are 8 or 16-bit. There are a fixed number on each chip, and each one is of a fixed type. So you might have an 8-bit timer and a 16-bit timer, or some combination of them. You can trigger an interrupt for an overflow, or you can trigger an interrupt at a fixed value. So you might want to have it, instead of counting all the way from 0 to 65,536, you might say, well, I want to trigger an interrupt 2/3 of the way through that. And the reason you might do it at some arbitrary amount is because it takes a certain number of clock cycles to get there. And if you're trying to do it based on the time, you work out how many clock cycles and how many increments it's going to need to take that amount of time, and then you put that in as the overflow counter instead of just letting it count through to the end. As I said before, it can trigger changes directly in certain pins. That's actually a hardware function, which is why PWM is only available on some pins. It's because those pins are the ones that happen to have been hooked in to the hardware timers that are available on that chip. There are also different counter modes. The counter modes I'll get into in a second. One of the things that comes as an advantage of doing the timer control manually, if you have a servo, say, that needs a particular duty cycle, maybe it's not just it has to be on 50% of the time to move to a certain point. Maybe it needs to be on 50% of the time, but it needs to be in 10 millisecond blocks or 5 millisecond blocks. Otherwise, it won't do it. You can't have that level of fine-grained control with the Arduino library. It just says, well, this is what you get. If you want something more specific than that, great. You can do it yourself this way. So the timer modes are just different ways of counting in the documentation for the chips. It's shown as a waveform, and they're called waveform generation options. So what you have is the normal one, which is just sort of counting up, hits overflow, back down to 0. You have CTC, clear timer on compare. So this is where you can say, I want it to count until 20,000, and then reset back to 0. You can have fast PWM, which will do the same sort of sawtooth thing, but it will potentially set a hardware pin at a certain value, and then when it gets to overflow, reset that pin back down to 0. And so that's probably the method that is being used for PWM on your normal Arduino boards. The phase-correct PWM is almost the exact same thing, but instead of overflowing the top, it actually starts counting back downwards again, and will toggle the pin again as it passes the OCR0A value on the way down. OCR0A is just the name of a register that you put a value into. In this case, it's the overflow compare register for timer 0. The A is just a suffix because if you have, say, a 16-bit timer, you might need A and B because they're 1 byte each for the registers. Timer registers, okay. So there's a whole bunch of timer registers, and this is the sort of hairier stuff. So in this example, we've got TCCR 0A and B, which is for the timer counter 0, control register A and B. Sometimes you need 2 registers, sometimes you need 3 registers. It depends on what chip and which timer and what options that are available on that timer as to how many bits of configuration it needs. Those bits control the waveform generation, whether it goes directly outputting to a pin or not, the clock selection, so whether it uses an external source like a crystal or an incoming video feed, and the prescaler. The prescaler is because, if you're running on an 8 megahertz machine, even if it's just tiny little chips to 8 megahertz, so you don't want to count necessarily to 65,535 one per clock cycle, because that's really, really fast, right? So maybe you only want to do it every 1,024 clock cycles. So there's a series of prescalers which basically just divide the clock by that speed and let you slow down that counting. Between choosing the overflow or comparison values and choosing a prescaler, you can actually pretty closely map to most real-world times that you might care about. TCNT, so that's the timer counter for, in this case, timer 0 again. This is the value, or one of the values like TCNT0 would be getting read by the millis function, which would be set up to have 1 clock tick per millisecond or thereabouts. OCR0A, I've already mentioned, is the comparison value. So if you're only counting up to 20,000 and then resetting, that's it. Or if you're doing PWM and it's toggling the pin every time it passes that point. The timer interrupt mask, much like when we talked about interrupts, this is just to say, I want to have timer interrupts enabled for, well, this particular timer. So let's tie it all together. Right, so some includes, nice and easy. Main function. I've actually got a copy of this code in a GitHub repo, and it's got even more comments and links to the actual parts of the data sheet that you need to care about. So by all means, after this, go and clone the repo. It's got a copy of the presentation as well if you actually want to read it again for some crazy, crazy reason. Yeah, so the first thing you do is we set up the data direction register, and I do it, as I said before, there's a binary OR, and I'm setting DDB1 and DDB2, which on the actual pin package are pin 15 and 16, which happen to be next to each other. I set port B to 0, so that wipes out that whole set of 6 or 8 pins, all back to low. I call a function to set up a timer, which we'll get to in a second, and then I enter my infinitely awesome loop. Because we do all of the handling in this sample program in an interrupt, because that's absolutely the worst way of doing it, so I thought it was awesome to do. Well, it's a good example anyway. So, I've commented out at the top there, CLI. CLI, normally you use it to turn off the interrupts so you can set up the timers without worrying about timer interrupts happening behind your back while you're mid-configuration. In this case, the chip is just booted, so it's not actually on anyway, but just so you don't forget it. So you read through the data sheet and it's got TCTR 1A, and there's a whole bunch of boxes that say, for the 8 bits of this register, these are what the options are, and if you set 1 in these particular boxes, that means this, and if you set 1 in these particular boxes, that means that. So in this case, I didn't want any of those boxes set, so I just set the whole register to 0. Those boxes for this particular timer 1A on a ATmega328, sets a normal waveform generation, so it just counts up to overflow and then stops. And is not set to tie up to go directly to a pin. And register B for that timer, again, no waveform options because they ended up being split across the 2 because there wasn't enough room in 1 byte for all the options there. So there's no waveform options, but I do set a clock prescaler. So CS11 and CS10 are both bit numbers in that register that are named in the data sheet. Read the data sheet, it says if you want a clock prescaler of 64, you set CS11 and CS10, and that's exactly how to do it. And again, this has a 3rd register for setting up timer 1 because there's a whole bunch of extra options and we don't want any of them. The final thing, as I said before, I want to enable timer overflow interrupt for timer 1. And then we turn on interrupts entirely. So when I was writing the sample code for this, I actually I forgot that last line and spent a lot longer than I'd like to admit trying to work out why my timer wasn't counting, and it turned out my timer was counting fine, but the interrupt was never triggering. So yeah, don't forget that. So this is the actual timer interrupt. So timer 1 OVF without the underscore is mentioned as the name of the interrupt in the data sheet. So you just put the underscore in yourself, write underscore vec on the end, ISR is the macro. Among other things, when you do this, it sets up a sort of prepends and appends a bit of code around your function to turn off interrupt handling, again at the top, and turn it back on at the end, because you don't want to interrupt your interrupt handler, because then bad things will happen. So that's the end. No. So we still have to build it. So I showed a brief line before, and that is the fuller line. Well, that's a full make file that's actually fully capable of building the application on the previous slides. In this case, you'll see I've also got a flash target in make, and that just runs AVR dude with -C USB tiny, because that's the class of ISP that I have. Says I want to flash this type of chip with this type of controller. The -U flash :W, that's, so -U is upload, and then you have to say what you want to upload to. So in this case it's flash, you can upload directly to EEPROM and things like that. Flash, I want to write, and I want to write this file to it. And so that file is a dependency of the flash target, and that gets compiled by the rest of the gibberish at the bottom that I can barely read. So depending on your actual setup, you may have to, and in my case at the moment on my laptop, because I've just reinstalled, have to do sudo make flash, because I haven't actually set up my permissions so that I have access to the USB device for the ISP as my own user. So the last thing about Arduino is community. So the Arduino forum is obviously a really good community resource, and there's sections for people wanting to do all sorts of stuff. And the thing is, you don't need to go after that, right? There is no after that. This stuff, all of the handling interrupts and timers and ports and pins and I/O and that, you can do all of that within the Arduino IDE, with Arduino libraries being used for other things, on a regular Arduino Uno or Freetronics Leo stick or whatever it is that you happen to have. And you might just say, for this particular thing, I need manual control of a timer. For this particular thing, I want to have some custom interrupt handling. For this particular thing, I need to actually set all of these pins at the same time because it's connected to a really finicky LCD controller, and if I update them 3 or 4 clock cycles apart, it doesn't like me. So this is all after Arduino, but it's all still Arduino. So there's no problem with still going back here and talking about this stuff. There's also a lot of good blogs around for doing all sorts of different things, either with Arduinos, with AVR chips directly, or even just with things that are nothing to do with either of the above. Sites like Hackaday and plenty of others. And there's us, there's the Arduino community and the greater programming community at places like LCA, where we have Arduino Mini-Conf for a whole day. And we have all these extra Arduino and Arduino related talks all through the week, because it's something that we're all interested in and it's something that we can all learn from each other. The reason I said that I wanted to come up and do this talk to the organisers when they were asking for papers was because this is a talk that I would have loved dearly to have seen last year. Because last year, I opened my bag, a bag of goodies, swag bag at the start of the week, and I got out the Leo stick and I said, this is actually a lot of fun when I started playing with it. And I wanted to know more about it, and there were a bunch of code samples, but I couldn't understand half of them because they did some of the things in this presentation. They did interrupt handling, and things like that. So let's not forget that we can actually still interact with each other and learn from that. And all of these things are still here, even if you're doing them differently. So just starting to wrap up, appropriated, shared a whole bunch of photos from various places, all under either public domain or CC BY SA licenses, the same as the slide pack is. And again, if you want to tweet some abuse, that's the one there. So that's cool. So yeah, wrapping up, Arduino is the hardware, and we can go and we can take that hardware and do more and interesting things with different hardware. We can use little 8-pin chips, or we can just go and do deeper things. You can replace bits of the software, you can use the IDE, or you can just jump down and use GCC and make files. You can write leaner software and more specific software. You can still be part of the hacker community. And the code for the sample in this, that does compile after a while. And the PCB layouts for the little things, so you can plug your ISP directly in over the top of your chip, all available on that GitHub repo. Thank you very much. I'm happy.
Any questions?
Hi, I'm Alistair De Silva from Makehack Void. I'm one of the founders of the local hackerspace here. Not sure whether you saw my talk as part of the Arduino Mini-Conf, but a lot of the stuff that, actually pretty much all of the stuff you've discussed here, we've actually got wrapped up in a C++ library called MHBlib.
Yes, I actually think I did see that talk.
Okay. But just a couple of other things. The timers.
Yeah.
So the overflow registers are called A and B and sometimes C, not because they're 16 bits, but because they're actually different channels on the timer. So you can actually set 3 different values. You'll actually get 3 different interrupts coming off that timer as it cycles around.
Yep, I might have gotten confused between that and the register stuff.
And the other thing was the bit shifts. So AVR-libc actually has an _BB macro, which masks away all of that stuff, which makes the code a little bit easier to read, maybe.
It does. I did consider putting that in, but I actually prefer the way it reads this way because it sort of hides a bit less of what it's doing, and it's about the same length anyway. Just so you guys know, I have no idea what I'm talking about. Seriously.
As far as community goes, if you're programming Arduino stuff, you can go to the Arduino website. If you're programming directly AVR stuff for support, there's an IRC channel called AVR that's a good source of help if you're stuck.
Cool.
Yeah, that's #AVR. AVRfreaks.net is a website, or #AVR IRC channel on Freenode.
Cool.
So you're a bit more educated now than you were when you started out with all of this. I wonder if time's money, if you would have made a better investment in a bunch of Leo sticks?
time is money, but only money that you, only time that you can actually get money for. So this isn't something I've been doing for work. This is something that I've been doing for my own entertainment and my own education. So no, I wouldn't go back and buy a bunch of Lego sticks. Now that I've done this, I probably would. But I'm the sort of person that likes sort of going, what's under this cover, and trying to understand a lot better how things work.
Fair enough.
When you moved away from using the Arduino IDE and the inbuilt Arduino libraries, what sort of a hex payload or flash size reduction did you see in the images that were being flashed to the chip?
I didn't actually look at that. You'll save a couple of kgs by not having a bootloader. A lot of the stuff that I've been doing just in the straight AVR libc is actually to 80 tiny devices, so they're not ones that you can compile the full set for anyway.
If there are no more questions, thank you very much for your talk, and I'd like you to accept this gift from Linux Australia and the organisers.
Thanks very much.